Whew. It's going to be a very short class. There's a reason why I put 14 and 15 together. Element of the day, argon. I don't know what people really use argon for. It can absorb a lot of energy for a gas. People put it in between double pane windows for that reason. Helps to keep the cool inside and the hot outside, or the hot inside and the cold outside. I really picked it as a finisher to illustrate what it isn't. The noble gases are inert. Unlike all the other elements, salts are formed from stuff on the left-hand side of the periodic table of elements and stuff on the right-hand side of the periodic table of elements. Sodium, chlorine. I keep on talking about how the chemical properties of elements change completely as they gain and lose one proton, so they can attract an extra electron or they lose an electron. But compounds' chemical properties change completely too. Sodium explodes in water. Your body's 80% water or something like that. Chlorine is a deadly gas. Sodium chlorine is a salt that you eat all the time, your body needs. So the left-hand side gets together. The right-hand side is called an ionic bond. Another type of bond is called covalent, where electrons are shared. I'm not going to really get into this. It's chemistry, not astronomy. Astronomy makes elements. When elements get together, it's a chemist domain. I just wanted to cap it off real quick with either a reminder or else to titillate you with your new idea. Urge you to take chemistry at some point. Unit 15, the end. For the class and of the universe. So, cosmology is the science that studies the large-scale structure of the universe. How did it end? How did it change as it grew? What's going to happen eventually? Right now, the universe is expanding. Not only is it expanding, but it's expanding faster and faster all the time. Touched on that a lot in Unit 14. What could cause the universe to slow down? Gravity. Gravity pulls things together. Could cause the universe to speed up? Well, theoretically, anything we haven't taken into account yet. But we know one thing for sure, it is speeding up. And we don't know why. So, if gravity were to win, which right now it very much looks like it's not going to, everything would have expanded out from a central point, and then eventually would slow down and it'd all come back together. The big crunch. When I was an astrophysics student back in the day, people considered the big crunch to be a viable possibility. This might really happen. Nowadays, we don't think that it's on the table at all. One thing that prevents gravity from winning is that the universe just isn't that dense anymore, because stuff isn't close to each other. The overwhelming force of gravity can't get it to be back together. The critical density is the density that the universe would have to have in order to not come back to a big crunch, but just slow down and for everything to stay where it is. And that's not going to happen either. So continue forever. The universe is at a critical density. Everything's getting further apart, but at some point it just ends up in a balance. No, that's not the way it's going to go. Not unless the laws of physics change, which they might. If the laws of physics don't change, what's going to happen is something called the big chill. The universe is not dense enough. It expands forever. It doesn't slow down. Right now it's accelerating. And that looks like our eventual fate. And because not only is space getting bigger and the distance between things getting bigger, but the rate at which space is getting bigger appears to be accelerating, eventually only gravitationally balanced systems will stay together. So if you fast forward tens of billions of years, the only part of the universe we'd be able to reach or access would be our local group, which by that point will have all collided to form a big elliptical galaxy. Gonna skip all that. Gonna skip the cosmological constant. Not gonna talk about what's making the universe accelerate. But again, something is. We don't know what is causing the universe to accelerate. We call it dark energy. And it is a complete mystery. But one thing we know about dark energy is that it's not a constant. The amount of dark energy the universe is generating seems to change epoch to epoch. If the amount of dark energy the universe is creating remains a constant, great. Everything gets distance, but gravity is still able to win. And by win, I mean is able to hold galaxies that are close to each other together. If dark energy becomes stronger and stronger and stronger, then at some point, the expansion of space is going to be strong enough that it can rip apart chemical bonds, that it can rip apart galaxies, that it can rip apart planets. That would be the big rip scenario. And if dark energy just suddenly peters out, then maybe gravity could start to win again, and we could have the parts of the universe that can still see each other gravitationally collapse. But that is not something that anybody considers to really be on the table. Whatever it is dark energy is going to do, it's always been with us, and there's no reason to think that it would disappear. So dark energy stays roughly where it is now. Galaxies will get very, very far apart until we can't see any other galaxy besides the Milky Way and the other galaxies that have collided with us. By that point, we would have absorbed Andromeda, or because Andromeda is bigger than the Milky Way, it's probably more accurate to say that Andromeda would have absorbed us, would have absorbed the Triangulum galaxy and eaten a bunch of the minor galaxies around here. Stars in the Milky Way will continue to form at a decreased rate every year, but we will have star formation for a while. But eventually, we'll run out of gas. And even those M-type stars that live for 100 billion years will cease to do fusion. And then we're in a new era of the universe, an era without stars. But as far as we know, time will not stop. Time will march on. So we have a universe that's full of white dwarfs slowly cooling off, neutron stars slowly cooling off, and black holes slowly evaporating. Ironically, given that the black hole is the most massive of the type of corpse a star can leave behind, it is the only one of these objects that we expect to go away someday. If Hawking radiation is real, then black holes will eventually, in the very, very, very far future, cease to exist. By that time, the neutron stars and the white dwarfs would be the same temperature as the rest of the universe, which will, by that point, only be a handful of millikelvin. Right now, it's about 2.7 Kelvin, which is cold, super cold. So cold, we have to turn cartwheels to make it be that cold on Earth. But it's not impossibly cold. The universe will continue to chill until it reaches temperatures that we can't achieve in the laboratory on Earth. And everything will be that temperature. If protons are stable and decay, eventually these dead stars would turn to black holes and they would evaporate themselves. But we've been running a lot of really sensitive experiments to see if protons do decay, and thus far we haven't found one decaying yet. So it's starting to look unlikely. Protons are starting to look stable. Our guesses about the exact age of the universe depends on its expansion history. In the beginning, it was expanding super fast. And then it continued to expand, but less quickly. And now it is expanding, but the rate of expansion is increasing. So there's three factors that influence how this is going: the amount of matter slowing down the expansion, the amount of dark energy speeding up the expansion, and the shape of space-time. There's three possible shapes of space-time. It could be flat, which is what we think it is. It could be open, or it could be closed. I'm not going to make you worry at all about what these geometries mean, because I could talk for a solid 20 minutes and it would still be confusing. I can't draw you a picture of what the universe would look like if it were flat or curved or open. I only offer you the analogy I offered before. If the universe is open and you shine two lasers perfectly parallel, the curvature of space-time will make them eventually cross. Oh, sorry, if the universe is closed, the curvature of space-time will make them eventually cross. If the universe is open and you shine two laser beams perfectly parallel, then the universe will eventually diverge. The laser beams will eventually diverge like this. And if the universe is flat, then they will travel parallel for forever. In that case, the best way I can describe the structure of space-time is that it's like a weird four-dimensional hyperdonut. If you find that confusing, so do I. And if you don't find that confusing, I'm impressed, because I do. But that's the most detail we're going to get into it. We don't know what dark matter is. And we don't know what dark energy is. But we know that as far as energy content in the universe is mostly dark energy. And then after that, it's mostly dark matter. And then after that, it's mostly visible matter. So most of the energy content in the universe is bound up in things that we do not understand at all. Definitely not going through that. So in the very, very, very early universe, there was something called inflation, which is a period of rapid expansion immediately after the Big Bang that lasted a very short amount of time, much less than a billionth of a second. Why was there inflation? Well, we don't know. We also don't know if inflation was caused by the same thing that we currently call dark energy, or if it was something else. But inflation does solve a bunch of mysteries involving the universe, one of which I'm going to delve into, which is when the universe ceased to be a star, electrons were able to reattach to their protons, and photons were able to travel freely for the first time. The entire universe was very, very, very smooth. That implies really strongly that it expanded so fast that it lost touch with itself. If it were turbulent, if the universe were able to interact with itself very much in the early days, then we would expect that there would have been distortions that would have naturally arisen from that interaction. We would have ended up with a universe in which maybe things don't look the same in all directions due to systems coupling with other systems. But we don't see that at all. The universe looks exactly the same, or almost exactly the same in every direction. That means that the universe went from being like this to being relatively huge extremely quickly, before any of the different parts of the universe had time to really talk to the other parts of the universe. So yes, quantum mechanics says the early universes should have had huge fluctuations in temperature from place to place. This is kind of like what two liquids would look like if they were dumped into a badly mixed bag. Big clumps of clear liquid here, big clumps of orange liquid there. The universe expanded too quickly before these fluctuations could have had time to smooth out. Not going to talk about the horizon problem, not going to talk about the magnetic monopole problem. I'm not even going to go through this because I haven't done enough work to do the background for it. So here's our universe today. It's 4.6% atoms, 23% dark matter, 72% dark energy. We have no idea what dark energy is. We just know the universe is behaving in a certain way. And the only way for it to behave that way is if space-time itself is generating a certain, you can think of it as a pressure. We call that pressure dark energy. It's making things fly apart. Dark matter is attractive. It's making galaxies rotate in a way that we can only explain by hypothesizing that most galaxies are sitting inside of the halo of something we call dark matter. We don't know what it is. Atoms we can see though. And so we hypothesize the presence of dark matter and dark energy based on what atoms are doing. And as far as the things that have gravity, 63% of it is dark matter. 10% would be neutrinos, those non-interacting particles that fly out in nuclear reactions. 15% of the energy would be light itself, photons. Photons also have energy and a gravitational field. And 12% would be gravity, or atoms. We unravel these mysteries by flying protons around super fast and colliding them into each other, watching what flies out, how we figure out what the structure of matter is. That's called particle physics. And this is the biggest accelerator in the world, CERN. It's in Geneva, Switzerland. And that's about all I can tell you about the state of cosmology without doing a lot more legwork. But I can address some of the questions that we don't really have answered. Why did the Big Bang happen? No idea. Is it the only Big Bang to have happened? No idea. Is our universe the only universe? No idea. There could be a multiverse. We could not say. This is why this is a very, very, very short lecture. And the finer feature of the solar system I'm going to talk about, the Oort cloud. There's probably something out there. We see a bunch of comets with really, really big orbits and random orientations relative to the sun. The Kuiper Belt's made up of comets, but they're all in the ecliptic. So when comets come out of the Kuiper Belt, they're more or less in the same plane that planets orbit in. The reasonable conclusion is that there is a huge sphere, not a belt, but a sphere of icy bodies hanging out a bit less than a light year away from our sun, but still gravitationally bound to our sun. We can't see it. They're too little, they're too dim, but we see comets coming in from that spot. Usually they plow straight into the sun. Hopefully none of them will plow straight into us. If the Kuiper Belt exists, it will look something like this.
Short period comets visit the sun so often that they quickly evaporate, vanishing in only a few 100,000 years.
Short period comets are largely from the Kuiper Belt.
Here's one that evaporated in the sun's corona in July 2011. It was traveling at 644 kilometers per second. That's 400 miles per second. Here we see it in time lapse from the Solar Dynamics Observatory. The comet enters on the right in this video. In this second pass, I've marked it along the way. It starts out with the mass of an aircraft carrier, and it's completely evaporated in 20 minutes by the searing heat of the sun's corona. They evaporate so quickly, compared to the age of the solar system, that we shouldn't see any left at all. Yet, we routinely track dozens of them every year. In 1951, Gerard Kuiper proposed that there must be a belt of icy bodies orbiting beyond Neptune that is the source for new comets. It is much further away, much larger, and far less dense than the asteroid belt. It starts at 30 astronomical units from the sun and is 20 astronomical units wide. 1992 QB1 was the first Kuiper Belt object. In 2002, a large KBO, hundreds of kilometers in diameter, named Kuawa, was found. In 2004, KBO Sedna was discovered. And we have seen that Pluto and Makemake are dwarf planet KBOs. It is estimated that the Kuiper Belt contains 100 million comets. In 1950, in order to explain long period orbits, the Dutch astronomer Jan Oort proposed the existence of a cloud of comets between 5,000 and 55,000 astronomical units from the sun. Other estimates have it going out much further. All estimates put the Oort cloud well outside the heliosphere. Oort estimated that this reservoir contains 100 billion comets, maybe 1 trillion. Sighting Spring, Hale-Bopp, and Lovejoy 2014 are 3 of them. No space probe has yet been sent to the area of the Oort cloud. Voyager 1 in the heliosheath is traveling at 1.6 million kilometers per day. That's 1 million miles per day. It will take over 1,200 years just to reach the Oort cloud, and over 12,000 years to pass through it. So its existence will remain a theory for some time to come.
And
You're not a dish.
that was it. No more class. Let me stop the recording.